Hello students, this is my ninth lecture with you. Today we shall see initial value problem, boundary value problem and their solution by the method of separation of variables. First, what is initial value problem and boundary value problem? In any application of ordinary differential equation or partial differential equation, in case of physical or engineering problems, the problem generally involve a differential equation, ordinary or partial, and one or more supplementary conditions, which the solution of the differential equation must satisfy. If all the associated supplementary conditions relate to only one value of independent variable or variables, the problem is called an initial value problem, IVP in short, or one point boundary value problem. One point boundary value problem means initial value problem. The associated supplementary conditions relate to only one value of independent variable or variables, that is at one point. If the associated supplementary conditions relate to two different values of independent variable or variables, that is at 2 points, the problem is called a two-point boundary value problem or simply a boundary value problem, BVP. Okay. For example, dy by dx equal to minus x by y with the condition y bracket 3 equal to 4. That is y equal to 4 when x equal to 3. The solution takes the value 4 when independent variable x takes the value 3. So this is a differential equation with one condition at one point. So it is an initial value problem. Ordinary differential equation it is. Roman 2, del z by del x equal to 16 del z by del y, partial differential equation. Condition given is z0y equal to 4 into e to the power minus 5y. Condition is at the point 0y, that is x takes the value 0 and y is y arbitrary. In that case z is 4 into e to the power minus 5y. So under this condition, this is the partial differential equation considered. So this is an initial value problem, IVP. And Roman 3, d square y by dx square plus y equal to 0. Second order ordinary differential equation under the conditions y0 equal to 1 and y pi by 8 equal to 5. That is y is 1 when x is 0, y is pi by 2 when x is 5. Two conditions, 2-point conditions. Conditions are given at 2 points. So this is an example of boundary value problem. Also del square z by del x square equal to 1 by c square del square z by del t square. Z is dependent variable, x and t are independent variable here, and the conditions z0t equal to 0, zat equal to 0. That is value of z at the point 0t and at the point at are both 0. So conditions given at 2 points. That's why this is a boundary value problem. Now, Dirichlet boundary condition or first type boundary condition is a type of boundary condition when imposed on an ordinary or partial differential equation, it specifies the values that a solution needs to take along the boundary of the domain. That is, for one dimension it may be at the endpoints of the interval, and for two-dimensional, three-dimensional at the along the boundary of the surface represented by the solution. Okay, an ordinary differential equation or partial differential equation together with Dirichlet boundary condition is a Dirichlet type boundary value problem. So a Dirichlet boundary condition means it specifies the values that a solution needs to take. Function takes, solution is a function takes values, specified values along the boundary of the domain. So this is Dirichlet type boundary condition, and ODE or PDE together with Dirichlet type boundary condition is called a Dirichlet type boundary value problem. Newman boundary condition or second type boundary condition is a type of boundary condition when imposed on an ODE or PDE, ordinary differential equation or partial differential equation. The condition specifies the values in which derivative of a solution is applied within the boundary of the domain. That is, conditions are imposed on derivative of the function, derivative of the solution also, That is Newman type boundary condition. And ODE or PDE together with Newman boundary condition is a Newman type boundary value problem. In practice, a boundary value problem may be associated with both Dirichlet and Newman boundary conditions. Means the condition imposed on the solution may be values of the solution at some specific points or values of the derivative of the solution at some specific points. So that's a mixture. For example, describe by dx square plus lambda y equal to 0. Lambda is arbitrary constant with the condition y at 0 is 0 and y at pi by 2 is also 0. That is y equal to 0, y equal to 0 when x is 0 or pi by 2. 2 points. Conditions are given at 2 points. Del square y by del t square equal to c square del square y by del x square. Here y is dependent variable, x and t are independent variable. Y0 t is 0 and y at t is 0. Value of y at the point 0 t and at the point a comma t are both 0. A Dirichlet type boundary value problem. Dirichlet type boundary value problem because the conditions are only imposed on the solution of the differential equation. And describe by dx square plus lambda y equal to 0 with the condition y dash 0 equal to 0, y dash pi equal to 0. Value of the solution function derivative, value of the derivative of the solution function at x equal to 0 and at x equal to pi are both 0. So this is a Newman type boundary value problem. Also del square u by del x square plus del square u by del y square equal to 0, Laplace's equation. This is called Laplace's equation in two dimension. With the condition u suffix x 0 comma y equal to u suffix x a comma y equal to 0 means partial derivative of u with respect to x at the point 0 y and at the point a comma y are both 0 when y varying from 0 to b. Restriction. Partial derivative of u with respect to y at the point x comma 0 is 0, x varying from 0 to a. Partial derivative of y u with respect to y at the point x b is fx with the condition, extra condition, that is x ranging from 0 to a. This is also a Newman type boundary value problem. Conditions are imposed on derivatives, and of course okay, so that's why this is a Newman type boundary value problem. In practice, we shall get, of course, mixture of this derivative condition and also condition on the solution function. Now, method of separation of variables for solving PDE or solving boundary value problems or initial value problems. This method is based on the assumption that the substitution z equal to x into y, x of x into y of y, means capital X is a function of x alone, capital Y is a function of y alone. So this method is based on the assumption that the substitution z equal to x of x into y of y reduces the given PDE with z as dependent variable and small x and y as independent variables to two ordinary differential equation for capital X and y respectively. And after this substitution z equal to xy, capital X into capital Y, the given PDE will reduce to two ordinary differential equations involving capital X and Y as dependent variables and small x and y as independent variables. And if capital X is equal to phi of small x comma c1 and capital Y equal to psi of small y comma c2 are solutions of those two ordinary differential equations, then the complete solution of the given PDE is given by z equal to xy, that is phi of x comma c1 into psi of y comma c2. This is for a PDE with one dependent variable and two independent variables, and of course the process may be generalized for 3 or 4 independent variables also. Let us see solution of some examples by this separation of variables method. Solve the PDE x into del z del x equal to del z by del y using method of separation of variables. The PDE is x into del z by del x equal to del z by del y. Let z equal to capital X into y, where capital X means x of x is a function of small x alone and capital Y means y of y is a function of small y alone. Therefore, del z by del x is dx by dx, d capital X by d small x into y. Here y is a function of y alone, so when we differentiate partial with respect to x, that will be constant. And dx by dx, capital D capital X by d small x, let us denote it by x dash, capital X dash into y. Now del z by del y, similarly capital X into dy, d capital Y by d small y, derivative of capital Y with respect to small y, equal to x into y dash, capital Y dash. Dash here denotes derivative with respect to x or derivative with respect to y, as the case may be. Therefore the PDE number 1 becomes x small x into capital X dash into y, capital Y, equal to capital X into capital Y dash. Or we can write it x small x into capital X dash by x, equal to capital Y dash by y. See, the variables are separated. Left side functions of small x alone, right side functions of small y alone. So LHS of this number 2 is a function of small x alone and independent of y, no y in the left side. And also RHS of number 2 is a function of small y alone and independent of x, right side no x. So both LHS and RHS must be equal to a constant, because left side is independent of y, right side is independent of x, but these two ratios are same, equal. Two sides are equal, so both of them must be equal to a same constant, otherwise this will not hold. So therefore small x into capital X dash by capital X equal to k, and capital Y dash by capital Y is equal to also k. So from this, capital X dash by capital X equal to k by small x, and capital X dash means d capital X by d small x, derivative of capital X with respect to small x, by capital X is k by x. Right side is also d capital Y by dy, derivative with respect to small y, equal to k. And now it is d capital X by x, and this right side is k by x dx, separation of variable for ordinary differential equation. Capital X and small x separated. Here also d capital Y by y equal to k into dy, small dy. Okay, variables are separated, ordinary differential equation. Therefore integrating we get both sides integration given, integrating constant log c1 and their integrating constant log c2. So it is log capital X equal to k log x plus log c1 and log y equal to ky plus log c2. So it is log x minus log c1 means log x by c1, and here we can write it log small x to the power k, laws of logarithm, and here also log capital Y minus log c2 means log y by c2 equal to ky. Therefore from this line x by c1 is x to the power k, but c1 is crossed at the same time, so it is capital X equal to c1 into x to the power k, and y equal to c2 into e to the power ky. Therefore complete solution of given PDE is z equal to capital X into capital Y, that is c1 x to the power k and c2 e to the power ky. Values of capital X and Y substituted, or c1 into c2 can be taken as the product of two constant is single constant, let us denote it by c. So it is c into x to the power k e to the power ky, where capital C is c1 into c2 is an arbitrary constant. So this is the solution by method of separation of variables. In practical problems, C and K are determined from given boundary conditions. This is a theoretical problem. In practical problems, boundary conditions will be given, and from that we can find the value of C and K. Let us see example number 2. Solve by separation of variables method the PDE del z by del x equal to 16 del z by del y given z 0 y equal to 4 e to the power minus 5y. Value of z at the point 0 y is 4 into e to the power minus 5y. Initial value problem. So del z by del x is 16 del z by del y. Let z equal to capital X into capital Y be the solution, trial solution. This is the solution where capital X is a function of small x alone, capital Y is a function of small y alone. Therefore del z by del x is x dash y as before, del z by del y is x y dash. Therefore number 1 becomes x dash y equal to 16xy, implies x dash by 16x equal to y dash by y. Number 2. So since LHS of number 2 is a function of x alone and RHS of number 2 is a function of y alone, so we must have both the LHS and RHS equal to a constant, single constant k, say. Therefore x dash by 16x equal to k, y dash by y equal to k, and x dash means dx by dx by capital X is equal to 16k, and y dash means dy by dy small y by capital Y equal to k, and then separate the variables. Dx by x equal to 16k dx, dy by capital Y is k dy, integrating as before, it is log x, log c1 integrating constant, side changed. Here also log c2 side changed. Log m minus n is log m by log n, means here log x by c1 is 16kx, log y by c2 is ky. So capital X is x by c1 is e to the power 16kx, so capital X will be c1 e to the power 16kx, capital Y will be c2 e to the power ky. Therefore complete solution of the given PD is given by z equal to capital X into y, means c1 e to the power 16kx, c2 e to the power ky, means z equal to c e to the power k common 16x plus y, where c means c1 into c2 is arbitrary constant. Now given condition is that z0y equal to 4 e to the power minus 5y. Value of z at the point 0y, x0, the value is 4 e to the power minus 5y. Therefore if we put here in this solution x equal to 0, what we get? z0y, it is c e to the power ky, c e to the power ky, and z0y is given 4 e to the power minus 5y. So 4 e to the power minus 5y is c e to the power ky. Therefore from this comparing we get c equal to 4 and k equal to minus 5. Therefore particular solution is z equal to e to the power minus 5 bracket 16x plus y. So this is the particular solution of the IVP, initial value problem. It is an initial value problem involving partial derivative. And okay, number 3, example number 3, solve the PD, this PD py cube plus qx square equal to 0 by the method of separation of variables. Py cube plus qx square equal to 0, or y cube del z by del x plus x square del z by del y equal to 0. Let capital Z equal to capital X into Y. Capital X is a function of x alone, capital Y is a function of y alone. Therefore as before, del z by del x is x dash y and del z by del y is x y dash. Therefore putting these values in number 1, we get y cube x dash y plus x square x, small x square into capital X into y dash 0. So side change, then separate the variables, x dash by small x square x equal to minus y dash by small y cube into capital Y. Therefore as before, both these sides of number 2 must be equal to a single constant. So x dash by x square x equal to k, y minus y dash by y cube y equal to k. K is a constant. Therefore x dash means dx by dx, d capital X by d small x, and y dash means d capital Y by d small y, derivative with respect to y here. So separate the variables again, d capital X by x and kx square dx right side, and here d capital Y by y equal to y cube ky cube, it is with minus sign, minus ky cube. Yes, it was missed. So minus ky cube dy, d capital Y by capital Y equal to minus k small y cube dy. Therefore integrating, this is log x, integrating constant log c1, integration kx square dx is kx cube by 3, here it is minus ky to the power 4 by 4, log c2 side change, so it is log x by c1 is k by 3x cube, and here it is log y by c2 is minus k by 4, k cube by 4, y to the power 4. So therefore x equal to c1 into e to the power k by 3x cube, and y equal to c2 into e to the power minus k by 4, y to the power 4. Therefore complete solution of the PD is given by z equal to xy equal to c1 into e to the power k by 3x cube into c2 into e to the power minus k by 4, y to the power 4. So c1 c2 let us take as c, so c into e to the power k by 3x cube, law of indices, minus k by 4y cube, so you can take k by 12 common, so it becomes c into e to the power, c into e to the power, so this is missed, c into e to the power k by 12 4 x cube minus 3 y to the power 4. C is arbitrary constant, so boundary conditions not given, that's why this is the solution, general solution or complete solution. We stop here. Example number 4, show that z equal to 4 e to the power minus 3x into cos 3y is a solution to the boundary value problem BVP, del square z by del x square plus del square z by del x square equal to 0, Laplace's equation in two dimension, under the condition zx comma pi by 2 equal to 0. zx comma 0 is equal to 4 e to the power minus 3x. The two boundary conditions are given on the function value, solution value of the solution. So this is a Dirichlet type boundary value problem. So given PD is del square z by del square plus del square z by del square equal to 0. Let the solution of this PD is given by z equal to xy, where x, capital X, is a function of x alone, y is a function of y alone as before. Therefore, del z by del x is x dash y, del square z by del square will be x double dash y. This x double dash, capital X double dash means d square x by dx square. Del z by del y is xy dash, del square z by del y square is capital X into y double dash means d square capital Y by dy square, second derivative. Therefore, number 1 becomes x double dash y plus x y double dash equal to 0. So just side change and divide, we get separating the variables x double dash by x equal to minus y double dash by y, which is possible. This equality is possible if both sides of number 2 are equal to a single constant k, say, because left side is a function of small x alone, right side is a function of small y alone. Therefore, capital X dash by capital X equal to k and minus y dash by y double dash by, kx double dash, capital X double dash by capital X equal to k and minus y double dash by y equal to k. It is a plus symbol. Okay. Therefore, this x double dash means d square x by dt square, x crossed equal to kx, and here d square y by dy square equal to minus ky. So side change, d square x by dx square minus kx equal to 0. Here d square y by dy square plus ky equal to 0. So these two are second order ordinary differential equation with constant coefficients. Therefore, auxiliary equation here it is second order, d square. So it will be m square minus k equal to 0, means m square equal to k. And here it is auxiliary equation will be d derivative square here is there, so it will be m square plus k equal to 0, so m square equal to minus k. Now there are various cases depending on the sign of k. Case 1, if k is positive, let k equal to s square, positive real number, so k equal to s square. Therefore, from 3, m square equal to s square implies m equal to plus minus a, roots of the auxiliary equation plus minus a. Therefore, capital X equal to, means solution of this number 3, capital X equal to c1 e to the power ax plus c2 e to the power minus x. And for 4, m square equal to minus s square. So m equal to plus minus ia, complex roots, 0 plus minus ia. So alpha is 0, beta is a here. So the solution of number 4 is second order linear differential equation ordinary. So it is y equal to c3 cos ay plus c4 sin ay, because independent variable is here y, and alpha is 0, so e to the power alpha y is not necessary here. So it is c3 cos ay plus c4 sin ay. Now case 2, if k is negative, let k equal to minus s square. Then in this case, capital X means this time m, for number 3, m will be complex roots. So solution will be x, capital X will be c1 cos x plus c2 sin x, and k minus s square. So the roots of auxiliary equation in for number 4 will be plus minus a, means this time capital Y is c3 e to the power ay plus c4 e to the power minus ay, just interchanged the solutions in the previous case. If k equal to 0, case 3, then 3 and 4 become d square x by dx square equal to 0, d square y by dy square equal to 0. Therefore, integrating 2 times we get, if one time if we integrate dx by dx small x, it will be c1, and then if we integrate, it will be c1x plus c2. Similarly, d square y by dy square is equal to 0. If we integrate once, it will be dy by dy, d capital Y by d small y equal to c3, another constant, and then integrate c3y plus c4. Therefore, various possible solutions of the PDE number 1 are z equal to product of capital X and Y in case 1, product here z equal to product of x and y in case 2, and this is product of x and y in case 3. 5, 6, 7 possible solutions. Now, which of these solutions satisfy the given boundary conditions? That we shall take as answer. This happens in PDE. There are many solutions for the same differential equation depending on various cases, and depending on boundary conditions we shall get the unique solution. To solve one under the conditions z at x comma pi by 2 0 and z at x comma 0 is equal to 4 e to the power minus 3x. These are the boundary conditions given. We can see again in the question. Zx comma pi by 2 0 and zx comma 0 is 4 e to the power minus 3x. So when y is 0 from number 5, let us see this solution 5 first. When y is 0 from number 5, what we get? Zx0, this condition, Zx0 is c1 e to the power x plus c2 e to the power minus x. Y0 means sin 0 is 0, here cos 0 is 1, so c3 only. So it will be c3, and Zx0 value is 4 e to the power minus 3x, so 4 e to the power minus 3x substituted, and here it is c1 c3 e to the power x plus c2 c3 e to the power minus x. Therefore, comparing, we get both sides c2 c3 is equal to 4 and a equal to 3, so that we get the first term exponential function, and this c1 c3 e to the power x, this term should be 0, means c1 c3 0, e to the power x never 0, so c1 c3 0, but c2 c3 is 4, so c3 cannot be 0, therefore c1 is 0. Also, when y equal to pi by 2 from 5, zx pi by 2 is c1 e to the power x plus c2 e to the power minus x, and y is pi by 2 substituted. Now this zx pi by 2 is 0, and here a already we have got 3, so substituted a value substituted here, and then it is cos 3 pi by 2. Cos 3 pi by 2 is a is 3, so cos 3 pi by 2 is 0. Sin 3 pi by 2 is minus 1, so c4 into minus 1, c3 part is 0. So we have got from this line, and c1 is also 0, already we have got, so c2 e to the power minus 3x, c4 into minus 1 means c2 c4 e to the power minus 3x equal to 0, that is c2 c4 equal to 0, e to the power minus 3x never 0, but c2 c3 equal to 4, so c2 cannot be 0, therefore c4 should be 0 here. Therefore number 5 becomes z is equal to c2 e to the power minus 3x. Number 5 becomes c2 e to the power minus 3x into c3 e to the power cos 3y, using this value of c4, c1, c2, etc. And that is c2, c3. Value of c2, c3 is again 4, e to the power minus 3x cos 3y. And this was the solution as given in the question also. We have to show that this is the solution. Z equal to 4 e to the power minus 3x cos 3y. Okay. So number 5 has given us the solution. So thank you for today.